Hey everybody, my name is Chris, and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science, and in this video we're going to do an example of Stokes Theorem. So this is a theorem in vector calculus that helps us evaluate certain types of integrals. And in this example, we want to evaluate the integral over the closed path C of the vector f dot dr, where f, the vector f, is made up of the components 5y, negative 5x, and 3, and C, that little path that we're integrating over, is the trace of the cylinder x squared plus y squared equals 4 in the plane z equals 1. So what I mean by that is if you imagine the circle x squared plus y squared equals 4, now in 3 dimensions this equation actually describes a cylinder. So in 3 dimensions we actually have an infinitely tall cylinder, and we want to intersect that cylinder with the plane z equals 1. So essentially we're actually just going to get a circle of radius 2 centered at the point 0, 0, 1. Okay, and it's going to turn out that this z equals 1 is actually completely irrelevant, and all that really matters is that we have this x squared plus y squared equals 4. Okay, so anyway, what does Stokes' theorem actually say? So Stokes' theorem says that under certain conditions we can evaluate this integral here. We can evaluate this as follows. The integral of f dot dr is going to be given by the double integral over the corresponding surface S of the curl of f dotted with the outward unit normal vector, d capital S. Okay, so remember, curl is just one of the basic vector operations here, and then we're going to dot that with the outward unit normal. So in order to understand this, we have to know what is S. Well, S is the corresponding surface for our C here, and if C is the trace of the cylinder, x squared plus y squared equals 4 in the plane z equals 1, then S is actually going to be the entire disk. So S, let's write that over here. S is the entire disk the set of all x, y, z such that x squared plus y squared is less than or equal to 4 and z equals 1. Okay, so where C is the trace of this cylinder, x squared plus y squared equals 4 and the plane z equals 1, so basically it's the intersection of this infinitely tall cylinder with the plane z equals 1, then the surface S is actually the entire disk, so the boundary and the inside of the disk. All right, so in order to do this, we have to identify what is the curl of f and what is n. Well, n is actually pretty easy because here n is the outward unit normal, and because we have a flat horizontal plane, z equals 1, okay, and the fact that it's 1 is totally irrelevant. All that's really important here is that we have a flat horizontal plane. And because we have that, the outward unit normal vector n is going to be 0, 0, 1. Assuming that our surface is oriented upwards, which if we're not told otherwise is pretty much a good assumption we can make, just to keep things simple. So again, the outward unit normal is 0, 0, 1, because it's pointing outward in the direction that the surface is oriented, and it's a unit vector because its length is 1. Now we also have to figure out curl of f. So how do we do that? Well, let's go to page 2 where we have the curl formula. So remember, in general, if we have a vector f that's made up of the components p, q, and r, where p, q, and r are actually functions of x and y and z, then the curl of f is the cross product of the del operator with f, and remember that's given by the partial derivative of r with respect to y minus partial of q with respect to z in the first component, and the second and third components are made up as follows. Partial of p with respect to z minus partial of r with respect to x, and then partial of q with respect to x minus partial of p with respect to y. Now in our case, for the specific f that we have, remember we have f equals 5y minus 5x and 3. Okay, so 5y is our p, minus 5x is our q, and 3 is the r. So in our case, we are going to have curl of f equals, now what's the partial of r with respect to y? Well, r is just a constant, so any derivative of that's going to be 0. And then we're going to subtract the partial of q with respect to z. Well, q is just a function of x, so the partial of q with respect to z is 0. What about the partial of p with respect to z? Well, p is just a function of y, so p, the partial with respect to p, or excuse me, the partial of p with respect to z is 0. And then we're subtracting the partial of r with respect to x. Again, r is just a constant, so that's going to be 0. And then we have the partial of q with respect to x. Now here, q is a function of x, so if we take the partial of this with respect to x, we get minus 5. And then we're subtracting the partial of p with respect to y, and p is 5y, so the partial of that with respect to y is 5. So we have negative 5 minus 5. And we see that the curl of f is just 0, 0, negative 10. That's actually pretty good news because that's a relatively simple vector there. So let's go back to page 1, and we're pretty much out of room here. So let me go ahead and erase this. And what we have left to do is actually not that much, so we can squeeze it into the room that we have here. So what I want to do now is use this formula here. So we're going to do the double integral over s of the curl of f dotted with the outward unit normal. So remember from the second page that the curl of f, so we have the double integral over s of the curl of f, which is 0, 0, negative 10, dotted with 0, 0, 1 ds. Okay, and if we take 0, 0, negative 10 and do the dot product of that with 0, 0, 1, then what are we going to get? Well, we're just going to get 0 times 0 plus 0 times 0 plus negative 10 times 1. And that's just going to simplify to negative 10. So this dot product here is just negative 10. Whoops. So then our integral actually becomes the double integral over s of negative 10 ds. Now let's pull out the negative 10. We have negative 10 times the double integral of s ds. Now what's this? Well, remember that thing I erased, it actually described what s is. S, remember, is the entire disk, x squared plus y squared less than or equal to 4. So basically s, what is s? S is a circle of radius 2. So if s is a circle of radius 2, what does this represent? This represents the area of that circle. And what's the area of a circle with radius 2? Well, it's going to be pi times the radius squared. The radius is 2, the radius squared is 4. Pi times 4 is 4 pi. So this is negative 10 times 4 pi, which gives us a final answer of minus 40 pi. And that's our final answer there. So again, if we went too quick there at the end, I'll just recap that real quick. So what we did was we said, all right, well, the double integral over s of ds just gives us the area of the region s, and the region s is just a circle of radius 2, because s is the entire disk, x squared plus y squared less than or equal to 4, inside of the plane z equals 1. So it's just a circle of radius 2, and that's pretty much it. And a circle of radius 2 has area 4 pi, so that's why this integral is 4 pi. And then 4 pi times the negative 10 that we got from the dot product gives us negative 40 pi. Okay, so this has been an example of using Stokes Theorem to evaluate an integral. And I hope you found this video helpful, and thank you for watching.